This is Peter's sled friction problem, which he requested me to do tonight. A girl coasts down a hill on a sled, reaching a level surface at the bottom with a speed of 6.8 meters per second. The coefficient of kinetic friction between the, I guess that means the sled, and the snow is 0.044, and the girl and the sled together weigh 620 newtons. If the acceleration of gravity is 9.8 meters per second, how far did the sled go before it came to a stop? So in order to solve this problem, we're basically going to need to have two different big things here. A force diagram and our variables of awesomeness. With those things, we should be able to fill in the gaps for the information that we don't know and organize the information that we do know. Okay, so what I've done here is basically filled out all of the information that the problem told us. So they told us that the force of gravity on the girl and the sled is 620 newtons, because that's what they mean by the word weight. Remember how that was a cuss word? When you see this word, it just means force of gravity. They told us the coefficient of friction is this number, which is mu, and we know the initial velocity is 6.8 and that she came to a stop, so final velocity is 0. And now we're trying to figure out the missing pieces of this force diagram, and eventually what we really want to find is delta x, how far she went before coming to a stop. So a very easy first step on this force diagram is if the force of gravity is 620, well, she's just going on flat ground and she's not accelerating up or down. So we know that the forces have to be in balance in the y direction, in the vertical direction. So the normal force here has to be 620 newtons. Now the only missing puzzle piece in this force diagram is the force of friction over here. And the way that we're going to figure that out is with a special formula that connects this goofy coefficient of friction to the actual force of friction. And that's the fun formula. So the fun formula says that the force of friction on an object is equal to the coefficient of friction, which we call mu, times the normal force. The normal force tells you how much contact there is between those two surfaces. So if we multiply those two together, we get a force of friction of 27.28 newtons. And that's going to be the net force because the force of friction is unchecked. These two forces cancel each other out, but friction stands alone in the x direction. So the net force here is 27.28. And when we know the net force, there's only one thing left to do. And that's using Newton's second law. If we know the net force, then we can figure out the acceleration. So we use F net equals ma, and the net force here is the force of friction, so 27.28 equals 62a. The way that I knew the mass was 62 is because the force of gravity is just 10 times the mass. So the sled and the girl have a mass of 62. So for mass, I plug in 62, and then I get an acceleration of minus 0.44 meters per second per second. The reason I put a minus there is because we know that the acceleration is going to make the thing slower, so it's opposing her current motion that's to the right. Now here's the crazy thing. All the work we just did on all this force diagram stuff, the only reason we did it, and the only reason we usually do it, is because we're trying to figure out what the heck the acceleration is, because forces cause accelerations. So if the acceleration is minus 0.44, we toss that answer over here on our variables of awesomeness, and now we have 3 of the boxes filled in. And if you know 3 of the variables of awesomeness, then you're going to be able to figure out the other 2. The one that we're particularly after here is delta x. So I'm looking for a formula that has a VI, a VF, an A, and a delta x in it. In this case, the formula that's going to do the trick is this one, because it has a VF, a VI, an A, and a delta x. So let's solve for delta x. If I toss the values in, then we get delta x equals 52.5 meters. Not a bad run.